4,530,000,000 kilometers from where you are sitting right now, something is breathing, not living, breathing. A haze of hydrocarbon particles rises each morning, drinks in a whisper of sunlight too faint to cast a shadow on Earth, and then exhales that heat back into the vacuum of space. Why would a world with almost no atmosphere at all need lungs? And why, when NASA's James Webb Space Telescope finally turned its 18-karat gold mirror toward this ice dwarf, did it find a chemical signature that matches nothing in any laboratory on Earth? Pluto was supposed to be a dead rock. It is not. On the 18th of February 1930, a 24-year-old farm boy from Kansas named Clyde Tombaugh sat inside a cold, unheated dome at the Lowell Observatory in Flagstaff, Arizona, blinking back and forth between two photographic plates on a machine called a blink comparator. He had been doing this for months, comparing thousands of star fields, night after night, hunting for the faintest possible dot of light that moved against the fixed background of the cosmos. That afternoon, a speck shifted. It shouldn't have. Stars do not move across two exposures taken 6 days apart, but planets do, and this one had shifted exactly the way a distant, slow-moving world would shift. Tombaugh had found Planet X, the mathematically predicted body that astronomer Percival Lowell had spent the last years of his life chasing and never lived to see. They named it Pluto after the Roman god of the underworld, partly because it lived in permanent darkness at the edge of the solar system, and partly, some said, because the first two letters happened to match the initials of the man who had started the search. For 76 years, Pluto held the title of the ninth planet. Children memorized its name in the same breath as Neptune's. Then, on the 24th of August 2006, in a Prague conference hall, the International Astronomical Union voted on a new definition of what a planet actually is, and Pluto failed the test. It did not clear its neighbourhood of other orbiting debris. The Kuiper Belt, the vast frozen ring of icy bodies beyond Neptune, was simply too crowded with rivals for Pluto to claim dominance the way Earth or Jupiter does. Overnight, Pluto became a dwarf planet. I find it, honestly, a little absurd that an object hundreds of millions of kilometres wide, with 5 moons and an active atmosphere, can be stripped of a title by a show of hands in a hotel conference room. But that vote set the stage for one of the most stubborn scientific comebacks in the history of planetary exploration. Because 9 years before that vote, in January 2006, a spacecraft the size of a grand piano had already left Earth, screaming away from Cape Canaveral atop an Atlas V rocket at just over 58,000 kilometers per hour, the fastest launch speed ever achieved by a human-built object at that point. It was called New Horizons, and its principal investigator, a planetary scientist named Alan Stern, had spent the better part of 2 decades fighting NASA's budget committees just to get it built. New Horizons would spend 9.5 years crossing the solar system before it reached its target, and it arrived at Pluto on the 14th of July 2015, 9 years after Pluto had already, on paper, stopped being a planet. Stern never accepted the demotion. He still doesn't. But that argument, satisfying as it is not really the story here. The story is what New Horizons found when it got there. It found a heart, literally, a vast, pale, nitrogen ice, plane-shaped unmistakably like a heart, 1,600 kilometers across, that scientists named Tombaugh Regio, in honour of the man who had discovered the whole world 85 years earlier. It found mountains of water ice standing 3,500 meters tall, jostling for space beside glaciers of frozen nitrogen that appeared to be flowing in real geological time, like the ice sheets of Antarctica. It found evidence of possible cryovolcanoes, ice volcanoes, that may have erupted in the last few million years, an eternity by human standards but a blink of an eye in planetary terms. None of this fit the story astronomers had told themselves for decades. That Pluto, sitting at an average distance of 59 billion kilometers from the Sun, receiving roughly 1/1000th of the sunlight Earth receives, should be a frozen, static, geologically dead world. It manifestly was not. And then there was the atmosphere. Pluto has one, a thin, tenuous shell of nitrogen, methane, and carbon monoxide gas with a surface pressure roughly 100,000th of Earth's, so delicate that it could theoretically freeze solid onto the ground during Pluto's 248-year orbit as it moves farther from the Sun. New Horizons instruments detected haze layers in that atmosphere, more than 20 distinct layers stacked like a layered cocktail, stretching up to 200 kilometers above the surface. Nobody expected a haze that structured, that persistent around a world that cold and that thin-aired. It was beautiful, it was strange, and it was at the time essentially unexplainable. New Horizons gave humanity its first real look at Pluto's face. But a flyby, by definition, is a glimpse, not a study. The spacecraft screamed past Pluto at over 49,000 kilometers per hour and kept going, deeper into the Kuiper Belt, leaving behind a single extraordinary dataset frozen in time, a snapshot of one season, one moment, one geometry. To understand Pluto's atmosphere as a living, changing system, to watch how it breathes across its seasons, how its haze behaves as the planet swings through its 248-year orbit, humanity needed a different kind of instrument. Not a spacecraft that visits once, a telescope that can watch patiently from 250,000 kilometers beyond the Moon. For as long as it takes, that telescope launched on Christmas Day 2021. It is called the James Webb Space Telescope, and it carries a primary mirror 6.5 meters across, built from 18 hexagonal gold-coated beryllium segments, sensitive enough to detect the heat signature of a bumblebee on the surface of the Moon. For years, JWST's target list was dominated by galaxies at the edge of observable time and exoplanets circling distant stars. Pluto, small, dim, and painfully close by cosmic standards, had to wait its turn. But when astronomers finally pointed Webb's infrared eye at that little world in 2022 and again in 2023, what came back did not simply confirm what New Horizons had already shown us. It rewrote the rules for how a planetary atmosphere is allowed to behave. And it left, sitting quietly inside the data, a signature that nobody, not one laboratory, not one database, not one theoretical model on Earth, could immediately explain. Here is the strangeness at the center of this story, stated as plainly as I can manage. On every other planetary atmosphere we have ever studied in detail, Earth, Mars, Venus, Titan, even Jupiter, the temperature of the atmosphere is controlled primarily by gas molecules, carbon dioxide, water vapor, methane. These molecules absorb and re-emit infrared radiation, and that exchange of energy is what determines whether an atmosphere runs hot or cold, whether it traps heat like a greenhouse or lets it escape into space. Gas does the work. Particles, hazes, dust, aerosols are usually just along for the ride, a visual effect layered on top of the real thermal machinery. That is the model. That is what nearly every atmospheric scientist trained on for the better part of a century. Pluto broke that model before we even understood it was broken. In 2017, a planetary scientist named Shi Zhang, working at the University of California, Santa Cruz, sat down with data from New Horizons and noticed something that did not add up. Pluto's atmosphere was far colder than the standard gas-driven models predicted it should be, colder by roughly 10 to 15 Kelvin, a discrepancy far too large to be measurement noise or rounding error. Something was cooling that atmosphere down beyond what nitrogen and methane gas alone could account for, and the obvious suspects, more of the same gas, at higher concentration, simply did not fit the observed profile. Zhang looked at the haze. Everyone had seen it in the New Horizons images, those photogenic, blue-tinted layers backlit by the sun, as the spacecraft looked back at Pluto after its flyby, an image that instantly became one of the most reproduced photographs in the history of planetary science. But haze, in the conventional wisdom, was decoration. Zhang proposed something else entirely. He suggested that the haze particles themselves, tiny grains of organic material, formed when ultraviolet sunlight breaks apart methane and nitrogen molecules high in Pluto's atmosphere and stitches the fragments back together into complex hydrocarbons, were not passive. He proposed that these particles absorb incoming sunlight during the day, heat up in the process, and then radiate that absorbed energy away as infrared light during the long Plutonian night, acting less like scenery and more like the atmosphere's actual thermostat. If Zhang was right, then Pluto's haze was not simply a byproduct of the atmosphere's chemistry. It was the primary engine controlling the entire planet's heat budget, a role that, as far as anyone had documented, no haze had ever been shown to play on any planetary body in the solar system. It was a crazy idea, Zhang would later admit, and he was not exaggerating for effect. When he first floated the hypothesis to colleagues, the reaction was politely, professionally skeptical. Planetary atmospheres are complicated systems with a great many moving parts, and after decades of consensus that gas molecules run the thermal show, asking your peers to accept that solid particles, essentially microscopic smog, were secretly in control of a planet's temperature was asking a great deal. It is worth pausing on this, because I think we forget how much scientific progress depends on someone being willing to look foolish in front of their peers for a few years. Zhang published his hypothesis anyway, in a 2017 paper in the journal Nature, and buried inside that paper was a testable prediction, the kind of clean, falsifiable claim that separates real science from speculation. If haze truly is cooling Pluto by radiating heat away, then that emitted energy should show up as measurable mid-infrared radiation, and any telescope sensitive enough in that part of the spectrum ought to be able to detect it directly. There was, in 2017, no telescope sensitive enough. Ground-based observatories struggle badly with mid-infrared work because Earth's own atmosphere is drenched in thermal noise at those wavelengths. Trying to detect a faint infrared glow from a world 4.5 billion kilometers away through the warm, turbulent blanket of Earth's own air is a little like trying to hear a whisper across a crowded stadium. Spitzer, NASA's previous infrared space telescope, simply didn't have the resolving power or the sensitivity for a target this small and this dim. Zhang's prediction sat there, published, waiting, testable in principle but untestable in practice. An open loop with no obvious way to close it. That is the position planetary science found itself in for the better part of 5 years. A bold, specific, falsifiable claim about how an alien atmosphere manages its own temperature, and no instrument on Earth or in orbit capable of putting it to the test. Meanwhile, other pieces of the Pluto puzzle kept accumulating, each one deepening the mystery rather than resolving it. Researchers noticed that Pluto's haze appeared in a striking bimodal size distribution, meaning the haze particles clustered into two distinct populations, small and large, rather than a smooth continuous range, a pattern documented in a 2022 paper by Siteng Fan and colleagues that added yet another layer of chemical complexity nobody had fully modelled. Other researchers found that the haze seemed to contain a significant fraction of actual ice, not just dry organic tholins, complicating the picture of what these particles were even made of. Every answer generated at least one new question, and none of the ground-based tools available could resolve them, because none of them could see Pluto's atmosphere glow. And there was a second, quieter mystery sitting alongside the haze question, one that had bothered scientists since long before Zhang's paper: Charon. Pluto's largest moon, at 1,212 kilometers across, is so massive relative to Pluto, roughly half its diameter, that the two bodies don't orbit each other in the way moons typically orbit planets. Instead, they orbit a shared point in space that sits outside Pluto's own surface, a genuine double world locked in a tight 6.4-day mutual dance, close enough that Charon appears to hang almost motionless in Pluto's sky. New Horizons revealed that Charon's north pole carries a distinct reddish stain, a discoloration scientists nicknamed Mordor Macula after Tolkien's Blackened Realm, and the leading hypothesis was that this red material originated on Pluto itself, methane gas escaping Pluto's thin atmosphere, drifting across the gap between the two worlds and freezing onto Charon's polar cap, where solar radiation then cooked it into complex reddish organic compounds. If true, this would mean that Pluto's atmosphere was not simply cooling and structuring itself in isolation. It was actively feeding material across space onto its companion world, a transfer of matter between two bodies that, as far as anyone could tell, happens nowhere else in the solar system, now where else. I want to sit with that phrase for a moment, because it is easy to let it slide past as a throwaway superlative. We have studied dozens of moons, hundreds of planetary and near-planetary bodies, across more than 60 years of space exploration, and this specific phenomenon, one world's atmosphere systematically painting the polar caps of its neighbour, has been documented in exactly one place. That singularity should unsettle you a little. It certainly unsettled the scientists trying to model it, because a mechanism this unusual demanded direct, repeated, long-term infrared observation to confirm, and in the years immediately following New Horizons, that kind of observation simply was not available. So here is where the story stood, for roughly 4 years. A hypothesis about haze controlling an entire planet's temperature, untested, a mechanism for cross-world atmospheric transfer, unique in the solar system as far as we know, undocumented. A bimodal haze structure with a chemistry nobody could fully explain, unresolved. 3 open questions stacked on top of each other, all converging on the same tiny, distant world, all waiting for the same thing. An infrared telescope powerful enough and patient enough to actually watch Pluto breathe. On Christmas morning 2021, the telescope left Earth. To understand why it took until 2022, and in some cases 2025 and 2026. For these questions about Pluto to even begin finding answers, you have to understand exactly how difficult it is to look at this particular world, and exactly how much had to go right with James Webb before anyone could even attempt it. Start with the numbers, because the numbers are the whole problem. Pluto's average distance from the Sun is roughly 9 billion kilometers, nearly 40 times farther than Earth. At that distance, sunlight arrives with roughly 0.09% of the intensity it has here. Noon on Pluto looks, to human eyes, something like a deep twilight on Earth, dim enough that you could still read a book, but nowhere near daylight. Pluto's own diameter is a mere 2,377 kilometers, smaller than Earth's moon, which means that from JWST's vantage point, roughly 1.5 million kilometers from Earth, at the L2 Lagrange point, Pluto's entire disk subtends an angular size of less than 1/10 of an arcsecond, a target so small and so faint that even Webb's extraordinary 6.5-meter mirror cannot resolve any surface detail on it whatsoever. Every single observation Webb has ever made of Pluto is of an unresolved point of light, a single averaged pixel representing the entire hemisphere facing the telescope. New Horizons could photograph mountains and glaciers because it flew directly past, within 12,500 kilometers of the surface. Webb, sitting nearly 6 billion kilometers away, cannot see a single crater. What it can do instead is something New Horizons never could. It can measure the precise spectral fingerprint of the light and heat Pluto emits across dozens of infrared wavelengths, repeatedly over months and years, watching how that fingerprint changes as Pluto rotates and as its seasons slowly turn. That capability depends almost entirely on one instrument aboard Webb. MIRI, the mid-infrared instrument built by a European consortium and NASA's Jet Propulsion Laboratory, and cooled to an operating temperature of just 7 Kelvin, about -266 degrees Celsius, using its own dedicated cryocooler, because even Webb's passively cooled optics, sitting behind a tennis court-sized sunshield, are not cold enough for mid-infrared work. Any warmth in the instrument itself would flood the detector with its own thermal glow, drowning out the whisper-faint signal arriving from a small ice world at the edge of the solar system. Getting MIRI that cold, and keeping it that cold, for years, without a single on-site repair opportunity 1.5 million kilometers from Earth, was one of the single largest engineering risks in the entire Webb mission. If MIRI's cryocooler had failed at any point, most of what I'm about to describe to you simply would never have happened. Pluto's secrets would still be locked away, an open question with no observational path forward. It didn't fail. And once MIRI was operating, teams of scientists, led primarily by Emmanuel Lelouch at the Observatoire de Paris and by Tanguy Bertrand, also at the Observatoire de Paris, submitted competing proposals for precious Webb observing time to study Pluto directly. Time on JWST is one of the most oversubscribed resources in modern science. In a typical observing cycle, astronomers request roughly 4 to 6 times more hours than the telescope can possibly deliver, meaning the vast majority of scientifically excellent proposals get rejected simply for lack of room on the schedule. Lelouch's proposal, Pluto's climate system with JWST, designated program GO 1658, made the cut. It secured time to observe Pluto's full mid-infrared spectrum, a spectral range running from 4.9 to 27.9 microns that no previous instrument had ever captured with sufficient sensitivity for a world this faint. The observations themselves were executed with almost surgical precision. In 2022, Webb captured light curves of Pluto and Charon at 18, 21 and 25 microns, essentially brightness measurements taken repeatedly as both bodies rotated, allowing scientists to map how temperature varies across their surfaces over time. Then, on the 4th of May 2023, MIRI captured something more ambitious, a complete high-resolution mid-infrared spectrum of Pluto and its atmosphere, spanning that full 4.9 to 27.9 micron range, with an exposure carefully timed to catch the planet's disk-averaged light at a specific rotational phase. This single spectrum, precisely the kind of data Xi Zhang's 2017 prediction had called for, and precisely the kind of data no instrument before Webb could have gathered, would become the foundation for answering, at last, whether his crazy idea about haze-controlled heating was correct. But here is where the story complicates itself again, because getting the data was only half the battle. Interpreting it required building an entirely new kind of climate model, one that didn't just track gas molecules the way every prior planetary atmosphere model did, but explicitly incorporated haze particles as active radiative agents, tracking how they absorb sunlight, heat, cool, and redistribute that energy through Pluto's thin atmospheric column. Bertrand's team had to combine the fresh JWST spectral data with Zhang's earlier theoretical framework and with sophisticated three-dimensional climate simulations of Pluto's atmosphere, the kind of modelling effort that normally takes years to mature, cross-check, and defend against peer review. Every discrepancy between the model's predictions and the observed spectrum had to be chased down individually. Was it a haze effect, a gas absorption line, an artifact of the instrument's own thermal background, or something genuinely unaccounted for in existing chemistry? And there was an added complication baked into Pluto's very geometry, because Pluto's rotation axis is tilted at roughly 122.5 degrees, meaning it essentially rotates on its side, more extremely tilted than any planet in the solar system except Uranus. Its seasons are savage, and its polar regions spend decades in either permanent sunlight or permanent darkness. Webb's observations captured Pluto at one particular point in its 248-year orbit, a snapshot of a single moment in an extraordinarily long seasonal cycle that New Horizons had only glimpsed for a matter of hours in 2015. Any model built from this data had to account for exactly where in that immense seasonal calendar Pluto currently sits, because the very quantity Zhang's hypothesis depended on how much sunlight the Hayes is currently absorbing, and therefore how much infrared heat it should currently be radiating, changes dramatically across Pluto's seasons. Get the seasonal context wrong, and the whole prediction collapses into ambiguity. It would have been entirely plausible, given all of this, for the JWST data to come back murky, a marginal detection, an ambiguous signal, the kind of result that generates a cautious paper concluding that further observations are needed, the most common sentence in all of planetary science. Zhang himself, by his own account, was not expecting quick, clean vindication. Most hypotheses in this field take a decade or more to confirm or discard, if they are ever definitively resolved at all. Careers have been built and ended on Pluto-adjacent predictions that turned out to be unfalsifiable with available technology, and there was no guarantee, none at all, that MIRI's single, hard-won mid-infrared spectrum of a world 6 billion kilometers away would contain a signal clean enough to settle a 7-year-old scientific argument. That is exactly, improbably, precisely what it did. When Bertrand's team finally finished processing the 2022 and 2023 MIRI data and compared it against their haze-inclusive climate models, the result was not ambiguous. It was not a marginal 3 sigma hint buried in noise, the kind of result astronomers learn to treat with professional suspicion. The mid-infrared thermal emission from Pluto's haze layer was strong, clear, and precisely where Zhang's 2017 model had said it would be. Their paper, published in Nature Astronomy on the 2nd of June 2025, titled Evidence of Haze Control of Pluto's Atmospheric Heat Balance from JWST Miry Thermal Light Curves, stated the conclusion in language unusually direct for a scientific journal. The haze particles suspended in Pluto's atmosphere are not passive decoration. They are actively, measurably, dominantly controlling the planet's entire radiative energy balance. The fundamental accounting of how much heat comes in from the sun and how much escapes back to space, the single number that determines whether a planetary atmosphere runs hot or cold, thick or thin, stable or chaotic. We were really proud because it confirmed our prediction, Zhang said when the paper was released. In planetary science, it's not common to have a hypothesis confirmed so quickly, within just a few years, so we feel pretty lucky and very excited. I want to underline how genuinely rare that sentence is in the culture of modern astronomy. This is a field where entire careers are spent chasing signals that never quite resolve. Dark matter candidates hunted for 40 years without a single confirmed detection, gravitational wave predictions that took a full century to verify, exoplanet atmosphere models debated for a decade before anyone gets close to consensus. A specific, falsifiable claim about how an alien world manages its temperature, published in 2017, tested directly by hardware that didn't exist yet, and confirmed within roughly 8 years of its original publication. That is, by the patient standards of this discipline, close to a sprint. Here is what the confirmed mechanism actually looks like, described as plainly as the physics allows. Sunlight, faint as it is at Pluto's distance, strikes the haze particles suspended tens to hundreds of kilometers above the surface. These particles, built from complex hydrocarbon and nitrile molecules forged when ultraviolet radiation splits apart nitrogen and methane gas high in the atmosphere, absorb that visible sunlight efficiently. The absorbed energy heats the particles directly, and because these are solid or semi-solid grains rather than gas molecules, they hold onto and re-radiate that heat differently than a gas would. They cool by emitting infrared radiation, largely at wavelengths Webb's MIRI instrument is specifically built to detect. On worlds like Earth or Mars, this same absorb and re-emit cycle happens, but it is a minor thermal player compared to the overwhelming influence of greenhouse gas molecules. On Pluto, with its vanishingly thin atmosphere and correspondingly weak gas-driven greenhouse effect, the haze particles are, for practical purposes, running the entire thermostat. The observed fluxes further indicated that this haze is composed of Titan-like organic particles mixed with hydrocarbon and nitrile ices, meaning the haze is not one simple substance, but a layered chemical cocktail, its composition telling its own story about the photochemical factory running in Pluto's upper atmosphere. That confirmation alone would have been enough to justify years of anticipation. But the same dataset, examined more closely, revealed something the original 2017 hypothesis had never explicitly predicted. The haze wasn't just controlling temperature in a static, steady-state way. It was rising and falling, behaving dynamically, its altitude and thickness shifting measurably between the two observation windows in 2022 and 2023. Evidence of an atmosphere actively cycling material vertically through its structure on timescales of months, not just millennia. Pluto's haze, in other words, isn't a fixed veil draped over the planet. It is closer to a living weather system, expanding and contracting, precisely the kind of behavior scientists associate with an atmosphere in active, ongoing chemical and physical flux, not the frozen, static relic most textbooks right up until this decade had assumed Pluto's atmosphere to be, and the JWST data confirmed something else that had until now remained speculative. the cross-world material transfer to Charon. By comparing the thermal light curves of both bodies against detailed surface models, Bertrand's team was able to place firm new constraints on the thermal inertia, essentially how efficiently a surface stores and releases heat of different regions on both Pluto and Charon. Those constraints matched the predicted pattern of methane gas escaping Pluto's atmosphere and depositing preferentially onto Charon's cold polar regions, adding hard thermal evidence to the visual case New Horizons had already made with its images of Charon's reddened Mordor macula. This is not a hypothetical anymore. Two worlds, locked in orbit around a shared point in space, are actively exchanging atmosphere for pigment. One world literally painting its neighbour in real geological time, using nothing but escaping gas and solar ultraviolet light as its brush and canvas. As far as the current scientific literature can tell us, this remains the only confirmed example of this kind of cross-body atmospheric painting anywhere in the solar system. There is a second layer to this revelation that deserves equal weight, because it reframes why any of this matters beyond Pluto itself. Xi Zhang made a point of connecting his confirmed haze mechanism to something much closer to home, early Earth. Roughly 2.4 billion years ago, before what geologists call the Great Oxidation Event flooded our planet's atmosphere with free oxygen, Earth's air was dominated by nitrogen and laced with hydrocarbon photochemistry, a composition startlingly similar in its basic ingredients to Pluto's atmosphere today. Life already existed on Earth during that ancient oxygen-poor era. In fact, many biologists now argue that this exact kind of nitrogen hydrocarbon chemistry, driven by ultraviolet sunlight, may have helped generate some of the organic building blocks that made life possible in the first place. By studying Pluto's haze and chemistry, Zhang explained, we might get new insights into the conditions that made early Earth habitable. This is, to my mind, one of the most quietly consequential sentences to come out of the whole body of research, because it suggests that the tiny, frozen, forgotten dwarf planet at the edge of our solar system might be running, in real time, a kind of natural laboratory experiment that recreates the chemical conditions of our own planet's deep, distant, life-originating past. But even as this confirmation closed one 7-year-old open question, it forced open several new ones, each larger than the last. If haze this actively controls Pluto's temperature, then what does that mean for Triton, Neptune's large icy moon, which hosts a broadly similar nitrogen-methane atmosphere and has never been studied with anything close to this level of infrared precision? What does it mean for the dozens of other Kuiper Belt objects we've only ever seen as unresolved points of light, whose atmospheres, if they have any at all, might be running on the same haze-driven thermal logic? And, perhaps most immediately pressing of all, if the haze itself carries this much chemical complexity, layered with hydrocarbons, nitriles and ices that don't cleanly match any single laboratory reference spectrum, then what, precisely, is this haze actually made of at the molecular level? That last question, innocuous as it sounds, is the one that would soon lead scientists to something they had not been looking for at all. A chemical signature with no known match anywhere in Earth's laboratory record, hiding in plain sight in the very same data that had just confirmed Xi Zhang's decade-old prediction. Science documentaries have a bad habit of talking about discoveries as if they simply arrive, as if data appears, conclusions follow, and nobody involved ever lay awake at 2 a.m. wondering if their life's work was about to be publicly disproven. I want to resist that habit here, because the Pluto story, more than almost any other in modern planetary science, is a story built from a handful of very specific, very human obsessions, and I think the discoveries mean more once you know the people who refused to let them go. Start with Alan Stern, because without his particular brand of stubbornness, none of the rest of this chapter, none of the rest of this entire script really would exist. Stern first proposed a dedicated mission to Pluto in the early 1990s, when he was a young planetary scientist arguing that the 9th planet, the only one never visited by any spacecraft, deserved its turn. NASA said no, then it said no again. Between 1992 and 2001, at least 5 separate Pluto mission concepts were proposed, funded partially, cancelled, revived, and cancelled again, victims of shifting budget priorities, changing NASA administrators, and a persistent institutional sense that a small, icy, arguably not even a planet body at the edge of the solar system simply wasn't a priority worth billions of dollars. I try to imagine what those years felt like from the inside, watching a mission you have designed, defended, and restructured again and again die in committee rooms you don't control, while the clock on Pluto's own atmosphere keeps ticking. Because here is the detail that turned Stern's persistence from stubbornness into genuine urgency. Pluto's atmosphere is not permanent. As the dwarf planet moves away from the Sun along its 248-year, highly elliptical orbit, its surface temperature drops, and at some point, nobody knows exactly when, possibly within a matter of decades, the nitrogen and methane gas in its atmosphere is expected to freeze directly onto the surface as frost, collapsing the atmosphere entirely until Pluto swings closer to the Sun again centuries later. Every year of delay in reaching Pluto was, quite literally, a gamble against a closing window that no human alive would see reopen. On the 29th of November 2001, after nearly a decade of failed proposals, NASA finally approved New Horizons as an official mission, largely credited to Stern's relentless advocacy alongside a coalition of scientists who refused to let the idea die quietly. Even after approval, the mission nearly collapsed again during a 2002 budget cycle, when the Bush administration's proposed NASA budget attempted to zero out its funding entirely, reversed only after intense lobbying from the planetary science community and, by several accounts, direct intervention from members of Congress who had been persuaded of the mission's scientific value. New Horizons finally launched on the 19th of January 2006, atop an Atlas V rocket, becoming, at the moment of launch, the fastest human-made object ever to leave Earth, departing at a velocity of roughly 16.26 kilometers per second relative to Earth. Fast enough to reach the Moon's orbital distance in just 9 hours, a trip that took Apollo astronauts 3 full days. Aboard that spacecraft, tucked into an aluminum canister on the upper deck, rode roughly 1 ounce of the cremated remains of Clyde Tombaugh, the farm boy from Kansas who had discovered Pluto 76 years earlier, and who had died in January 1997, 9 years before the spacecraft that would finally visit his discovery ever left the ground. Tombaugh's family donated the ashes at NASA's invitation, and Stern personally wrote the inscription engraved on the canister. Interred herein are remains of American Clyde W. Tombaugh, discoverer of Pluto and the solar system's third zone, Adele and Muron's boy, Patricia's husband, Annette and Alden's father, astronomer, teacher, punster, and stargazer. I find something genuinely moving in that detail, not because it's sentimental set dressing, but because it collapses the distance between the two eras of Pluto exploration into a single object. A man who discovered a point of light through a blink comparator in a freezing Arizona dome in 1930 was, 76 years later, physically present when a spacecraft finally reached the world he found. Carried there not by his own hand, but by scientists who had grown up idolizing the discovery he made, determined to close the loop he had opened. New Horizons reached Pluto on the 14th of July 2015, after a journey of 4.67 billion kilometers, passing within 12,472 kilometers of the surface at closest approach, traveling so fast, roughly 600 kilometers per hour, that the entire flyby's most critical data-gathering window lasted only a matter of hours, with no possibility of a second attempt if anything went wrong. The spacecraft was by that point so far from Earth that a radio signal took 4 hours and 25 minutes to travel one way, meaning mission control could not control the flyby in real time, even if they wanted to. Every instrument pointing, every image capture, every science sequence had been pre-programmed months in advance and uploaded to the spacecraft's onboard computer, and then Stern's team simply had to wait, through the flyby itself and through the agonizing hours afterward, for New Horizons to finish its silent automated data collection and finally phone home to confirm it had survived. Because of the encounter geometry, the spacecraft's high-gain antenna could not simultaneously point at Pluto for observations and at Earth for communication. New Horizons went completely silent during its closest approach, and Mission Control at Johns Hopkins Applied Physics Laboratory spent those hours not knowing whether their spacecraft, and the culmination of Stern's entire career, had survived the encounter or been destroyed by an undetected debris field around the Pluto system. When the signal finally arrived confirming a healthy spacecraft with a full data payload, the control room erupted. Footage from that room, Stern included, remains some of the rawest, most unguarded emotional documentation in the history of NASA public communications. Decades of frustration and risk dissolving into a single confirmed radio tone now shift the timeline forward, and the human story doesn't end, it simply changes hands. Zhang, publishing his Haze hypothesis in 2017, was not gambling billions of dollars or decades of career-defining advocacy the way Stern had. He was gambling something smaller but in its own way, just as personal, professional credibility, staked on a prediction he knew most of his peers found implausible, made testable only by a piece of hardware, the James Webb Space Telescope, that was, at the time of his 2017 publication, years behind schedule, billions of dollars over its original budget, and facing genuine public and congressional scrutiny over whether it would ever launch at all. Between 2011 and 2018, several members of the United States Congress proposed cancelling Webb outright, citing cost overruns that had ballooned the mission from an original estimated $1 billion budget to more than $9, $7 billion by the time of its eventual launch. Zhang's testable prediction, in other words, depended on a piece of infrastructure that was itself fighting for its survival. Through most of the years, his hypothesis sat unconfirmed. Two separate, precarious human projects, one an aging spacecraft racing a closing atmospheric window, the other a delayed, over-budget space telescope fighting congressional patience, had to both succeed years apart for this single scientific question to ever get answered. And then there is Tanguy Bertrand and Emmanuel Lelouch, the Paris Observatory scientists whose names appear as lead authors across nearly every JWST Pluto paper in this story, the Pluto's climate system with JWST proposal, the Haze confirmation paper, the atmospheric composition survey. Winning JWST observing time, as I mentioned earlier, is a competition with rejection rates north of 80% in most cycles. A proposal must not only be scientifically sound, but must out-argue hundreds of other equally credentialed teams, all fighting over the same finite hours of an instrument that cost NASA, ESA, and the Canadian Space Agency a combined total exceeding $10 billion to build and launch. Every hour, Bertrand and Lelouch's teams were awarded on Pluto came at the direct expense of some other scientists' proposal to study a black hole, an exoplanet, or a distant galaxy. A zero-sum allocation of one of humanity's most precious scientific instruments decided by peer review panels who had to be convinced, specifically, that a small, dim, forgotten dwarf planet deserved a slice of Webb's irreplaceable attention over everything else competing for it. I keep coming back to a particular thought while researching this chapter, and I want to say it plainly rather than bury it in narration. Every single fact I have shared with you so far in this script, the confirmed Haze mechanism, the material transfer to Charon, the ashes of a Kansas farm boy riding a spacecraft to the world he found, exist only because a small number of specific, named, mortal human beings refused, across nearly a full century, to accept not now or not worth it as a final answer. Clyde Tombaugh spent months at a blink comparator when he could have given up after week one. Alan Stern spent a decade rewriting proposals that kept dying in committee. Zhang published a hypothesis he knew his peers found implausible, and then waited 8 years to find out if he'd embarrassed himself. None of them knew, at the moment of their individual stubbornness, that it would work. That, I think, is the actual emotional centre of this entire story. Not the haze, not the infrared spectrum, but the fact that discovery this specific requires people willing to be quietly, professionally wrong in public for years, on the chance that they might eventually be right. They were right. But being right, as it turned out, was only the beginning of the next mystery, because buried in the very same JWST data that vindicated Zhang's haze prediction was a signal nobody had predicted at all, one that, as of this writing, remains completely unexplained. Let's widen the lens for a moment, because I don't think the true scale of what's at stake here becomes visible if we stay locked on Pluto alone. What Webb confirmed about haze-controlled atmospheric heating is not a piece of Pluto trivia. It is a direct challenge to a model of planetary atmospheres that scientists have relied on, in one form or another, since the mid-20th century, and once a foundational model breaks in one place, the responsible scientific response is to ask, urgently, where else it might be breaking that we haven't checked yet. Consider Titan first, because it is the most obvious next candidate, and because it is where the story actually widens into something stranger. Titan, Saturn's largest moon, is in many ways Pluto's atmospheric cousin. A nitrogen-dominated atmosphere, methane photochemistry, an organic haze produced by the same basic ultraviolet chemistry, but Titan's atmosphere is roughly 5 bar at the surface, 5 orders of magnitude denser than Pluto's, and its surface temperature sits around 94 Kelvin, compared to Pluto's roughly 37.5 Kelvin for nitrogen ice. If haze can dominate the thermal balance of an atmosphere as thin and cold as Pluto's, the immediate scientific question becomes whether a similar, if differently proportioned, haze effect is quietly at work inside Titan's much thicker atmosphere, an atmosphere we thought we understood reasonably well thanks to over a decade of direct observation by NASA's Cassini spacecraft and its Huygens lander, which touched down on Titan's surface in January 2005. If Titan's supposedly well-mapped climate has an underappreciated haze component too, then the confidence interval on nearly every climate model built from Cassini-era data just got a little wider for a world that remains one of the most tantalizing candidates for prebiotic chemistry, potentially even primitive life, anywhere in the solar system. And then there's Triton, Neptune's large retrograde moon, captured by NASA's Voyager 2 spacecraft in a single flyby in August 1989, and never visited or closely studied since. Triton hosts a thin nitrogen-methane atmosphere, strikingly similar in basic composition to Pluto's, complete with its own haze layers and active geysers of nitrogen gas erupting from its surface. Nobody has ever measured Triton's atmospheric heat balance with anything approaching the precision Webb just achieved for Pluto, which means an entire moon, one of the most geologically active bodies in the outer solar system, is currently sitting there with an atmospheric energy budget that scientists are, quite literally, guessing at, using models built on assumptions the Pluto data just proved were sometimes wrong. Zhang said it himself, plainly, we need to rethink their roles too. That is not a small sentence. That is a scientist telling you that an entire category of previously understood planetary atmospheres across the solar system may need to be re-examined from first principles, pliff the lens out further still, and the stakes climb again, this time off the map of our own solar system entirely. Every model astronomers currently use to interpret the atmospheres of exoplanets, the thousands of worlds discovered orbiting distant stars, many of them cold, nitrogen-rich, methane-bearing sub-Neptunes and rocky worlds sitting at the outer edges of their star systems, relies on the same underlying physics that Pluto's atmosphere just partially violated. If haze particles can seize control of a planet's thermal balance under the right conditions here in our own backyard, then any exoplanet atmosphere model that treats haze as a minor, secondary correction rather than a potentially dominant driver is working from an incomplete rulebook. This matters enormously for one of the biggest open questions in modern astronomy: the search for biosignatures in exoplanet atmospheres, the chemical fingerprints, oxygen, methane, ozone, in specific combinations that might indicate life on a world we will never visit in person, a world so far away that light from its star takes years, sometimes centuries, to reach us. If our haze physics is systematically incomplete, even for the most thoroughly studied dwarf planet in our own solar system, then every biosignature interpretation, built on similar assumed physics, for a planet 40 light-years away, carries a hidden margin of uncertainty that nobody had fully accounted for until this year. There's also a darker, more immediate implication worth naming honestly. Xizang's connection between Pluto's haze chemistry and early Earth's pre-oxygen atmosphere is not merely a poetic parallel, it's a genuine scientific tool, understanding precisely how nitrogen-methane photochemistry builds complex organic molecules, and precisely how those molecules interact with sunlight to control a planet's temperature gives astrobiologists an actual working model for what conditions might have looked like on early Earth roughly 3.8 to 4 billion years ago, the exact window during which life is believed to have originated and then survived its earliest, most fragile stretch of existence, entirely without the protective ozone layer or oxygen-rich atmosphere we now take for granted. If Pluto is functionally a frozen time capsule running a live simulation of early Earth-style atmospheric chemistry, a claim now substantially strengthened rather than merely speculated, thanks to Webb's confirmed haze mechanism, then every hour of JWST observation time spent on this small, dim, distant world carries genuine weight for one of the largest unanswered questions in all of science: how and under what atmospheric conditions life first became possible anywhere at all. I want to be honest here about something that I think gets lost in the excitement of a discovery like this. None of what I have just described resolves anything. It doesn't tell us whether life exists, or ever existed, anywhere beyond Earth. It doesn't tell us whether Titan's haze physics matches Pluto's, or whether Triton's does, or whether a single exoplanet biosignature interpretation needs to be revised. What it does is something quieter and, I would argue, more unsettling. It demonstrates, with hard observational evidence, that a physical mechanism scientists assumed was secondary, and minor turned out on at least one well-studied world, to be dominant and primary, and it leaves open the very real possibility that this same blind spot exists, uncorrected, in dozens of other atmospheric models currently in active use across the field. From moons in our own solar system to planets we will only ever know as a flicker of starlight passing through a spectrograph. That is the stakes ladder this discovery sits on. It begins as a confirmed prediction about one small world's temperature. It ends as a warning that an entire branch of planetary science may need to re-audit its foundational assumptions. At a moment when those exact assumptions are being used right now to search for signs of life on planets we cannot visit, cannot sample, and can only ever interrogate through exactly the kind of faint, easily misread infrared signal that just quietly overturned decades of consensus about a dwarf planet. Most people stopped thinking about the moment it lost its status as a planet in 2006. And it is precisely inside that same infrared signal, the very data that confirmed Zhang's haze prediction and reopened the Titan and Triton questions, that scientists found something else entirely. Something that did not confirm anyone's hypothesis. Something that, as of the most recent published research, still has no name. Everything I have told you so far in this script, however strange, has at least had an explanation attached to it by the end. The haze controls temperature. That's Xizang's confirmed mechanism. Charon gets painted red. That's escaping methane and solar ultraviolet chemistry. Even the bimodal haze particle sizes have a working theoretical framework. This chapter is different. This chapter is about the one piece of this entire investigation that right now, in 2026, remains genuinely, completely unexplained. And I think it deserves to sit at the centre of this script because it is the closest thing we currently have to a live, open scientific mystery unfolding in real time. Rather than one already tucked neatly into a settled paper, the story begins not with Pluto at all, but with Titan, and with a research program that was never designed to look for anything mysterious in the first place. Under a guaranteed time observation project designated GTO 1251, titled simply Titan Climate, Composition and Clouds, With Connor Nixon of NASA's Goddard Space Flight Center as principal investigator, JWST turned its near-spec instrument toward Titan on the 4th of November 2022. The goal was mainstream, well within the field's existing understanding. Characterize Titan's atmosphere, study its clouds, refine existing climate models. Nobody involved was hunting for an unidentified chemical signature. The instrument recorded a full spectrum spanning 0.95 to 5.27 microns, using an integral field unit that captures a 30 by 30 grid of tiny spatial pixels across Titan's disk, each roughly a tenth of an arcsecond across, an almost absurdly precise way to slice up the light from a moon nearly 1.4 billion kilometers away. Later, on the 11th of July 2023, the same program pointed Webb's MIRI instrument at Titan's leading hemisphere, capturing the complete 4.9 to 27.9 micron mid-infrared range, when a team led by Bruno Bézard at the Observatoire de Paris began combing through this data, focusing specifically on a narrow atmospheric window between roughly 4.9 and 5, 4 microns, a stretch of the spectrum where Titan's thick, hazy atmosphere is unusually transparent, giving rare direct access to light reflected off the actual solid surface beneath. They found something that shouldn't have been there. A clear, unmistakable absorption band, centered precisely at 5.113 microns, roughly 6 to 7% deep, appearing in both the NIR-SPEC spectrum and independently in the separate MIRI spectrum captured 8 months later, using an entirely different instrument, a different observing mode, a different hemisphere of the Moon. That independent confirmation across two separate instruments matters enormously, because it is precisely the kind of cross-check that rules out the single most common explanation for any strange signal in space telescope data, an instrumental artifact, a calibration quirk, a glitch in the detector electronics. Two independent instruments observing two different hemispheres at two different times both saw the same absorption feature at the same wavelength. Whatever this is, it is real. The team ran every check they could think of to rule out the mundane explanations first. Could it be residual methane absorption, some overlooked hot band transition hiding in this part of the spectrum? No. The researchers checked against a methane liner list built from first principles quantum mechanical calculations, precise enough that a real methane feature this strong and this localized could not have been simply missed. Could it be an artifact of atmospheric haze scattering, rather than a genuine surface signature? Here the researchers got clever. They compared the spectrum recorded at Titan's exact disk center against a separate spectrum averaged from the Moon's outer limb, reasoning that if the signal came from the atmosphere's haze layer, it should actually strengthen toward the limb, where the observing geometry forces light to pass through more atmosphere at a shallower angle. Instead, the absorption feature grew weaker toward the limb, roughly half as deep, while other known atmospheric absorption lines in the same spectrum stayed essentially unchanged between the two selections. That behaviour is the spectroscopic signature of a surface feature, not an atmospheric one. Something on the actual ground of Titan, not floating in the haze above it, is absorbing light at exactly 5.113 microns. Then came the part of the investigation that, to me, is the most quietly dramatic. In a completely separate observing program, GO 1658, the same Pluto's climate system with JWST proposal from Emmanuel Lelouch's team that had already produced the haze confirmation, MIRI had captured its full mid-infrared spectrum of Pluto on the 4th of May 2023. Bézard's team went back and checked that spectrum too, for a purely comparative reason. Pluto has an atmosphere strikingly similar in basic chemistry to Titan's, just far thinner and colder, so if this mysterious 113 micron feature really originated from some kind of nitrogen-methane surface chemistry, it might plausibly show up there too. It did, not faintly, not ambiguously, a broad absorption centered at 5.1128 microns, within measurement error of the exact same wavelength seen on Titan, but roughly 3 times wider and about twice as strong in total absorbed light. Two worlds, separated by roughly 3.5 billion kilometers of empty space, orbiting completely different planets under wildly different temperature and pressure conditions. Titan at a relatively balmy 94 Kelvin, with a surface pressure 5 orders of magnitude greater than Pluto's frigid 37, 5 Kelvin, and both of them carry the identical chemical fingerprint, at precisely the same wavelength, on their surfaces. I will admit, reading through the published paper describing this finding, I had to stop and read the same paragraph 3 times because the scientific caution in the language kept undercutting how strange the underlying fact actually is. This is not a case of two similar molecules producing two similar, slightly offset absorption bands, the kind of near-match scientists encounter regularly and usually resolve within a few pages of analysis. The two features sit at the same central wavelength, within a margin of just 0.0002 microns of each other, a precision so exact that Bézard's team explicitly ruled out coincidence as a plausible explanation. Whatever is producing this signal, it is very likely the same physical or chemical process, operating independently on two of the coldest, most distant surfaces in the solar system. So the obvious next question is simple: what is it? And this is where the paper, and honestly, the entire field, as of this writing, runs directly into a wall. The team methodically worked through the most likely candidates, and I think walking through this process is worth doing in some detail, because it shows exactly how much careful, patient elimination goes into a genuine scientific mystery before anyone is willing to call it a mystery in print. The closest apparent match at first glance was acetylene ice, a simple hydrocarbon, C2H2, already confirmed to exist in trace amounts in both Titan's and Pluto's atmospheres, with a known weak absorption band sitting at 1961 wave numbers, corresponding to 5.099 microns, tantalizingly close to the observed 1956 wave numbers, or 5.113 microns, but not close enough. Pure crystalline acetylene, measured in cold laboratory conditions around 80 Kelvin, also produces a much stronger secondary absorption band at 4.83 microns that simply does not appear anywhere in either the Titan or Pluto spectra, a glaring absence that argues strongly against pure acetylene as the culprit. Researchers even found laboratory measurements showing that acetylene ice diluted at low concentration in nitrogen shifts slightly in wavelength, but crucially it shifts in the wrong direction, moving further away from, not closer to, the observed feature. Acetylene remained on the list as a weak provisional candidate, but nobody involved considered it a confident identification. Next came benzene, C6H6, a molecule with a documented weak vibrational absorption mode sitting tantalizingly close to 5.11 microns in its solid state. But benzene's spectral signature comes as a package deal. In crystalline form, it shows two closely spaced absorption components rather than the clean single band observed on Titan and Pluto, and it comes paired with a second, similarly intense absorption feature at around 45 microns that is nowhere to be found in either spectrum. Critically, on Pluto specifically, this companion band's total absence allowed the researchers to essentially rule out pure benzene as the source there, though they left the door open, cautiously, for benzene mixed into some other chemical matrix on Titan, since laboratory work shows benzene's exact absorption wavelength can shift meaningfully depending on what molecular environment it's embedded in. Then propadiene, the simplest member of a chemical family called allenes, molecules built around a distinctive carbon-carbon-carbon double-bonded backbone, already directly detected in trace amounts within Titan's atmosphere itself. This looked, for a moment, like the strongest candidate of all. Propadiene shows essentially only one strong absorption feature in this exact spectral neighbourhood, unlike acetylene or benzene's messier multiband signatures, and its natural bandwidth in laboratory samples is narrower than the observed feature, meaning some plausible physical broadening mechanism, like variation in ice grain size, could in principle explain the difference. But the measured position was still off by roughly 10 wave numbers, a small-sounding gap that in high-resolution spectroscopy represents a real, unresolved discrepancy, not a rounding error. Pure propyrdine, in other words, sits close but not close enough to claim the match. Ketene, ordinarily an obscure candidate rarely discussed outside specialist ice chemistry literature, also came up. Its own weak solid-state absorption feature landing within a similarly frustrating near-miss range, close enough to remain plausible, far enough to remain unconfirmed. And hydrogen cyanide, HCN, a molecule with genuine astrobiological significance as a potential precursor to more complex prebiotic chemistry, was examined and specifically ruled out. Laboratory measurements across a wide variety of temperatures and molecular environments consistently place its key absorption band too far from the observed 113 micron position for it to be a serious contender, hydrogen bonding effects notwithstanding. What emerges from this careful, exhaustive elimination process is not a clean answer, but a clean absence of one. Bazar's team, in their published conclusion, state the situation with admirable scientific restraint. None of the known compounds catalogued in existing laboratory ice spectroscopy databases provide a convincing match to this signal on either world. Their favoured working hypothesis is not a specific molecule at all, but a category of explanation. Either a genuinely novel compound not yet characterised in any laboratory on Earth, or a known molecule so profoundly altered by mixing with other ices, or by being locked into an unusual physical state at the molecular scale that its familiar spectral fingerprint has shifted into unrecognisable territory. That second possibility carries its own quiet significance, because the paper's analysis of why the signal is roughly 3 times wider on Pluto than on Titan points toward exactly this kind of explanation, not a difference in temperature, since colder ices typically produce narrower absorption bands, which runs backward from what's actually observed, but a difference in molecular environment, the possibility that on Pluto's more heavily radiation-exposed surface, the cosmic rays penetrate centimetres to tens of centimetres into the ice. Due to the far thinner atmospheric shielding, the responsible molecule exists in a far more chemically diverse set of physical arrangements than it does on Titan's better protected surface. I find this genuinely haunting, and I don't think that word is an exaggeration here. We have, sitting in confirmed, cross-validated, peer-reviewed data from one of the most sophisticated scientific instruments humanity has ever built, a chemical signature appearing identically on 2 separate worlds, separated by billions of kilometres. And after systematically testing it against essentially every plausible known candidate compound in the published laboratory literature, the honest scientific answer is, we don't know what this is, not we have a leading theory that needs more confirmation, not there are 2 competing hypotheses, an open, acknowledged, published unknown, sitting in the data of 2 of the most well-studied icy bodies at the edge of our solar system, hiding in a part of the spectrum nobody had carefully examined until 2026, because it required exactly the right combination of instrument sensitivity, spectral range, and patient cross-comparison between 2 utterly different worlds that nobody had previously thought to line up side by side in quite this way. And there's a reason the discovery of Charon's own chemistry, made slightly earlier, deserves to sit alongside this mystery rather than in a separate footnote. In October 2024, a Southwest Research Institute team led by Sylvia Protopapa published the first detection of carbon dioxide and hydrogen peroxide on the surface of Pluto's largest moon, using JWST's NIRSpec instrument, observations taken across 4 separate viewing geometries in 2022 and 2023 that together provided full coverage of Charon's northern hemisphere. The carbon dioxide, the team concluded, most likely originates from Charon's interior, exposed at the surface through impact cratering events that punch through the overlying water ice crust, a discovery that adds real, physical evidence to the picture of Charon as a differentiated body with distinct internal layers, not a uniform ball of frozen water. The hydrogen peroxide is, in its own way, just as significant. It forms only when solar ultraviolet radiation and energetic particles from the solar wind and galactic cosmic rays break apart water ice molecules on the surface. and the resulting hydrogen and oxygen atoms recombine into this reactive new compound. Laboratory experiments conducted at Southwest Research Institute's dedicated ice chemistry facility confirmed that hydrogen peroxide forms readily under exactly these radiation conditions when carbon dioxide and water ice are mixed together, meaning Charon's surface chemistry is not simply inherited from its formation 4.5 billion years ago, but is being actively, continuously rewritten today, moment by moment, by cosmic radiation striking an airless moon with no magnetic field and no meaningful atmosphere to protect it. Put these two findings side by side, and the picture that emerges is not one of a dead, static Pluto-Charon system finally fully catalogued after New Horizons' 2015 flyby. It is the opposite. It is a system where every fresh application of high-precision infrared spectroscopy, Webb's confirmed haze mechanism, the cross-world material transfer, Charon's radiation-driven surface chemistry, and now this completely unidentified 5.113 micron absorption feature shared with a moon of Saturn nearly 1.5 billion kilometers away, keeps revealing active, ongoing, unresolved chemical and physical processes that nobody predicted in full, even after an entire dedicated spacecraft flew directly past and photographed the place in extraordinary detail a decade ago. The lesson embedded in this chapter, if there is one, is uncomfortable and I think exactly right. Proximity is not the same as understanding. New Horizons got closer to Pluto than any human instrument ever had, within 472 kilometers of its surface, and it still could not tell us what Webb's comparatively distant infrared spectroscopy, gathered from 6 billion kilometers away without ever resolving a single surface feature, has now revealed. Sometimes the deepest truths about a world are not written on its visible surface at all. They are written in the exact wavelength of light it chooses to swallow, and it took the right instrument, pointed at the right window in the spectrum, comparing the right two worlds side by side, to even notice the question existed. That question is still open. As of the most recent published research in 2026, nobody on Earth can tell you, with confidence, what is sitting on the surfaces of Titan and Pluto, absorbing light at exactly 5.113 microns. What we can tell you is that it is real, that it is shared between two of the strangest, coldest, most chemically active worlds in the outer solar system, and that finding out what it actually is will require something science has, historically, always eventually delivered, given enough patience, a closer look. Every open scientific question eventually collides with a practical one. What, precisely, is anyone planning to do about it? In the case of Pluto's newly confirmed haze mechanism and its unidentified 113 micron companion mystery, the answer splits cleanly into 3 separate timelines, each with its own constraints, its own risks, and its own reasons for hope. The nearest term path runs directly through Webb itself. Bazaar's team, in their published conclusion, explicitly flagged that a more extensive JWST dataset, additional NIA-spec observations of Titan at 4 different sub-observer longitudes, already gathered under a separate guaranteed time observation program led by Matthew Kamaka and Jonathan Lunine of Caltech and JPL, and slated for a dedicated forthcoming publication, should permit the first global mapping of this mysterious absorption feature across Titan's entire visible surface. Right now, scientists know the signal exists on both Titan's trailing and leading hemispheres, and that it appears roughly 3 times wider on Pluto's surface than on Titan's. What they don't yet know is whether it's uniformly distributed across Titan's geology or concentrated in specific terrain types. The dune fields, the lake beds, the mountainous regions Cassini mapped in such detail. If the signal turns out to correlate with a specific geological feature, that correlation alone would narrow the field of candidate molecules dramatically, the same way detectives narrow a suspect list by cross-referencing alibis against a timeline. For Pluto, similarly, additional Mirioi observations at different rotational phases and viewing geometries, the same kind of longitude-resolved approach already applied to the haze confirmation work, could reveal whether the 113 micron feature varies in strength across Pluto's surface, potentially linking it to specific terrain like Tombor Regio's nitrogen ice heart, or the older, more heavily cratered regions elsewhere on the dwarf planet. The midterm path runs through laboratories, not telescopes, and it is, in its own quiet way, just as demanding as any space mission. Bezar's team was explicit that resolving this mystery will likely require entirely new laboratory experiments. Synthesizing and measuring the infrared absorption spectra of specific candidate molecules, including complex alene compounds with varying chemical side groups, benzene mixed into different ice matrices, and other organic compounds not yet systematically catalogued at the extremely low temperatures relevant to Titan and Pluto, ranging from roughly 94 Kelvin down to as cold as 30 Kelvin. This is unglamorous, essential science. Technicians in facilities like the Southwest Research Institute's Class A laboratory or the IPAG facility in Grenoble, France, painstakingly growing ice samples of specific chemical mixtures under vacuum, chilling them to temperatures colder than anywhere naturally occurring on Earth, and then measuring precisely where and how strongly they absorb infrared light. Building, essentially, molecule by molecule, the reference library that space telescopes need in order to translate a mysterious wiggle in a spectrum into an actual chemical name. There is no guarantee this approach succeeds quickly. Some of the candidate molecules discussed in the published paper have simply never been measured under the exact combination of temperature, mixture, and physical state that Titan and Pluto actually present, meaning some of this foundational laboratory work is only beginning now. In 2026, years after the puzzling signal itself was first detected. The long-term path is the one with an actual, funded, in-progress spacecraft attached to it, and its name is Dragonfly. NASA's Dragonfly mission, a nuclear-powered rotorcraft lander roughly the size of a small car designed to fly directly through Titan's thick atmosphere and touch down at multiple separate sites across the Moon's surface, is currently scheduled to arrive at Titan in the mid-2030s, following a launch presently targeted for 2028. Dragonfly carries an instrument called DRAMS, the Dragonfly Mass Spectrometer, specifically designed to identify the chemical composition of surface and subsurface material by vaporizing tiny samples and analyzing the resulting ionized fragments. A technique fundamentally different from, and complementary to, the infrared spectroscopy Webb uses from a distance of 1.4 billion kilometers. In principle, DRAMS should be able to directly identify several of the leading candidate molecules proposed for the 113-micron feature, actually touching and sampling Titan's ice rather than inferring its composition from reflected sunlight. There is, notably, already a documented caveat buried in the discussion around this mystery. One of the leading candidate compounds, acetylene, is volatile enough that mission scientists have privately noted it may not survive intact through DRAMS's sample preparation and analysis process, meaning even a direct on-the-ground mission to Titan might not settle every open question this signal has raised. And Dragonfly, crucially, carries no equivalent infrared spectrometer capable of directly reobserving the specific 113-micron absorption feature itself in situ, meaning that even a fully successful Dragonfly mission may confirm the presence of a candidate molecule without ever directly connecting it back to the exact spectral signature Webb detected from orbit, leaving a frustrating gap between what the telescope saw and what the lander can prove. There is, notably, no equivalent dedicated mission currently funded to return to Pluto itself. New Horizons remains the only spacecraft ever to visit the dwarf planet, and it is now deep in the Kuiper Belt, continuing to send back data from increasingly distant objects, its plutonium power source degrading slowly but reliably, with mission engineers currently projecting operational capability into the early 2030s, before power constraints force the shutdown of its remaining instruments one by one. Proposals for a Pluto orbiter, a mission that would, unlike New Horizons' single fast flyby, remain in orbit around the dwarf planet for years, watching its atmosphere breathe across multiple seasons the way Webb can only glimpse from a comparatively enormous distance, have circulated within the planetary science community for years, championed by figures including Alan Stern himself. None have yet secured the kind of sustained funding commitment that turned New Horizons from a decade of rejected proposals into an actual launched spacecraft. Given the roughly 9.5-year transit time even a fast direct trajectory would require, and given the extraordinarily competitive landscape of NASA's current planetary mission budget, competing directly against sample return missions to Mars, potential landers to Europa and Enceladus, and continuing operational costs for Webb itself, any hypothetical Pluto orbiter proposed today would likely not arrive at its target before the late 2030s at the very earliest. And that assumes funding approval that has not, as of 2026, actually happened, which leaves us for the foreseeable future in a position that I think is worth sitting with honestly, rather than dressing up with false optimism. Webb will almost certainly continue its careful, patient observations of Pluto and Titan across the coming years, gathering the longitude-resolved data that might map this mystery signal across both worlds' surfaces. Laboratories will slowly, methodically expand the catalogue of known ice spectra, testing candidate after candidate against the stubborn 5.113 micron benchmark. Dragonfly will eventually arrive at Titan and sample its surface directly sometime in the mid-2030s, offering the first genuine ground truth chemistry from that moon in the modern era. But Pluto itself, the second half of this specific mystery, the world where the signal appears 3 times broader and twice as strong, will, for the immediate future, remain a point of light in Webb's field of view and nothing more, understood only through the patient, indirect language of absorbed and emitted photons 6 billion kilometers away, with no scheduled spacecraft, no confirmed budget, and no committed timeline to ever get closer again. I don't think that's a failure of the story. I think it's the story's actual, honest shape. Some mysteries get solved by the next mission, on a schedule we can name. Others get solved by the mission after that, decades from now, funded by people who haven't yet chosen this career, using instruments that haven't yet been designed. And some mysteries, like Zhang's haze hypothesis sitting untested for 8 years until exactly the right telescope happened to exist, simply wait, patiently, indifferently, at the edge of the solar system, for whoever eventually shows up with the right question and the right tool to finally ask it properly. There is a particular kind of silence that exists 5.9 billion kilometers from the Sun, and I don't mean the absence of sound. Space is silent everywhere, that part is not remarkable. I mean the silence of a place that has been waiting, without impatience, without any awareness that it is being waited for the tools capable of understanding it to finally exist. Pluto sat in that silence for 4.5 billion years before Clyde Tombaugh noticed its dot of light shift across 2 photographic plates in 1930. It sat there for another 85 years before a spacecraft finally photographed its mountains and its glaciers and its impossible heart-shaped plain of nitrogen ice. And it is sitting there right now, in this exact moment, still emitting a faint infrared glow at precisely 5.113 microns that no laboratory on Earth can yet name, patient in the specific way that only a world with no consciousness, no clock and no deadline can afford to be. I think there's something worth carrying with you in that patience, and it isn't really about Pluto at all. It's about the particular kind of human effort required to close the distance between not knowing and knowing. The months Tombaugh spent hunched over a blink comparator in an unheated dome, the decade Alan Stern spent rewriting a mission proposal that kept dying in committee, the 8 years Xi Zhang spent waiting to find out whether he'd built a career-defining insight or a career-embarrassing mistake. None of them got to skip the waiting. None of them got a guarantee at the outset that the waiting would end in vindication rather than silence. That, I suspect, is what real discovery actually costs. Not brilliance alone, but the willingness to stay curious about a small, cold, distant, unglamorous point of light for years, sometimes decades, on nothing more than the conviction that it might, eventually, tell you something true. We are, right now, at exactly one of those waiting points. The 5.113 micron signature sitting in both Titan's and Pluto's spectra is not a discovery with an ending. It's a discovery with a door left deliberately, honestly open. A signal confirmed real, confirmed shared between two worlds, confirmed to resist every known candidate compound in the published chemical literature, and confirmed, in the most literal sense, to be something humanity has never named. I don't think that should feel like a disappointment. I think it should feel like the opposite. Proof that even in a solar system we have supposedly already mapped, already visited, already reduced to Wikipedia info boxes and dwarf planet reclassification votes, there remains, hiding in a narrow window of infrared light on the coldest surfaces we know, something we have not yet figured out how to see clearly. What would it mean? I keep wondering, if that signature turns out to be something genuinely new to chemistry itself, not a known molecule wearing an unfamiliar disguise, but an actual compound that has never been synthesized, characterized, or even theorized about in any laboratory on Earth, existing instead only in the specific, brutal combination of near absolute zero temperatures, billions of years of cosmic ray bombardment, and nitrogen-methane photochemistry, that only these particular worlds at this particular distance from the Sun happen to provide. And what would it mean if it turns out to be something far more familiar, just profoundly reshaped by an environment human chemistry has never had reason to replicate? I don't think either answer, honestly, matters more than the other. What matters is that the question is still alive, still testable, still waiting for the next telescope pointing, the next laboratory experiment, the next mission that hasn't launched yet, carried by scientists who right now are still in school, still deciding what they want to spend their one life curious about. Science doesn't always give us endings. Sometimes it gives us horizons. And perhaps that's the entire point of a story like this one. Not to arrive at Pluto and declare it understood, but to keep the question of what's actually happening on its frozen surface alive long enough for someone younger, sharper, and more patient than any of us currently searching to carry it the rest of the way. Clyde Tombaugh handed his discovery to a generation he would never meet. Alan Stern handed his mission to a spacecraft that outlived his decades of advocacy and kept flying long after the flyby ended. Xi Zhang handed his hypothesis to a telescope that didn't exist yet when he first wrote it down. Somewhere right now, there is a scientist who will eventually hand us the name of whatever is sitting at 113 microns on the surfaces of Titan and Pluto. And they may not even know yet that this is the question they're going to spend their career chasing. We are the generation that noticed the signal. The name belongs to whoever comes next.